All right, hello Math 182 students. So this lesson is the lesson that I meant to give, of course, in our in last Thursday's class. And I can see that the homework for section 6.2, that most of you are pretty comfortable with the first set of exercises. And there's a lot of help aids and so forth. And given the discussion that we had before about volumes from section 6.2, I felt you'd be able to be fine with that overall. Naturally, see me at office hours if you have questions. And now we're working on more on section 6.2, more on volumes. And this will certainly help you with the second set of exercises from section 6.2. So let's take a look here at this example. And of course, since I'm recording this and I don't have a live audience, I won't be really pausing a whole lot. But you can always pause the video if you need to, right? If you're taking notes and so forth, which is a good idea. So in this first example, we want to find the volume of the solid obtained by rotating the region enclosed by the curves y equals x and y equals x squared about the x-axis. Okay, so of course we talked about this, that it's always good to make a picture of the volume you're looking at. Well, you have to make a picture of the region. The region is going to be enclosed by the line y equals x and the parabola y equals x squared. So if I go to the solution here, first thing I do is I make a picture. Okay, and don't worry about this terminology here. So here is this region bounded by the line y equals x, above by the line y equals x, and below by the curve or the parabola y equals x squared. And if you rotate that about the x-axis, you're going to get a volume that, well, it's an interesting kind of volume. It's again, this region, think of this region here, you're rotating about the x-axis, and it's going to generate a volume. Okay, and the volume is basically the difference. You can think of the volume as the difference between the volume of this cone and the volume of, maybe I'll put it in green, the volume, whoops, hold on. Yeah, the volume of this Hershey's Kiss here. So if you were to take away the volume of the cone generated by rotating the line y equals x about the x-axis, where x goes from 0 to 1, and subtract from that volume of the cone the volume of the Hershey's Kiss, which is generated by taking y equals x squared, that parabola, from x equals 0 to x equals 1, and then rotating that about the x-axis. So if you take the difference, you'll get the volume that you want. So this is a problem where I like to treat it like outer volume minus inner volume. So of course, in this problem, we learn that the volume is the integral of ax dx. Now hold on one moment on this. In section 6.2, you learn that the volume is equal to the integral of ax dx from A to B, and that's if you're rotating about the x-axis. You can also incidentally have, if you're rotating a region about the y-axis, you'd have the volume equals the integral from C to D, where the cross-sectional area is given by a function a of y. So in this case, we are going to be using this formula. And how do we get, so let me just write that formula down again. How do we get then this cross-sectional area? Well, if we were to, let's look at the cone. No, let's look at the Hershey's Kiss. If we were to take the Hershey's Kiss and cut it up into slices and look at the cross-sectional area of each slice, cross-sectional area would be a circle, right? Cross-sectional area, let me try to get this good here. The maybe I have to use my mouse, hold on. One moment. That isn't so good. Let me try it again here. That's a little better. Okay, so there's a cross-sectional area. There's a cross-sectional area, you know, A of X. And we want to find a formula for that cross-sectional area. So naturally, we need to find this radius here. Well, the radius goes from the x-axis to y equals x squared. And so the radius is x squared here. No, wait, I'm sorry. I'm on this here. I'm looking at the inner volume. The radius is x squared, and you're going to square that. So the radius right is pi. Radius of a circle is pi r squared, and we have a cross-sectional area here that is a circle, right? So the radius is pi r squared. Well, for the inner volume, the radius is equal to x squared. And incidentally, for the outer volume, if we were to look at the outer volume, okay, the outer volume also, you know, has a circle. I mean, what I'm trying to say is the cross-sectional area for the outer volume is also a circle. And the radius, let me just erase this here. The radius for that circle, let me just kind of draw it here. So another circle. Okay, and the radius for that circle is from here to here. So that radius is x. So you take x squared. You know, again, pi r squared. That'll get you that, like, you'll get the outer volume. Hold on. Yeah, you're going to have the outer volume minus this inner volume. So it's the cone minus the Hershey's Kiss, and those integrals are easy to work out, and you will end up getting 2 pi over 15. And that's what WebAssign wants. You know, WebAssign wants nice nice clean answers like that. Okay? All right, let's look at a few more problems here. Okay, so another example here. Now this time we're going to find an expression for the volume obtained of the solid obtained by rotating the region enclosed by the curves y equals x squared and x equals y squared about the line x equals -1. So in some of the earlier examples in section 6.2 in the textbook, they'll rotate a region about the x-axis, they'll rotate a region about a y-axis, but now we're rotating about a line, a vertical line, x equals -1. That's not the y-axis. Okay, it's 1 unit to the left of the y-axis. So these problems, since the cross-sectional areas are always going to be circles by virtue of the fact that we're rotating regions in a circle, what's critical is to find the radius, the necessary radii, okay, for the problem. So, and of course, to do that, it's necessary to draw a picture. So let's see what we have here. We have the curves y equals x squared and the curve x equals y squared, and we're going to rotate that about the line x equals, about the vertical line x equals -1. All right, I'm going to go to the solution, but just pause if you need to, slow down a little bit. One moment. Okay, thank you. So let us go to the solution here. Okay, so again, I draw a picture. And here's my parabola y equals x squared. Here's my parabola x equals y squared. Okay, and again, Desmos can draw that quite nicely. The intersection points are the origin and 1, 1. And this is the region I'm rotating about the vertical line x equals -1. So if I rotate that region about the vertical line x equals -1, then you can see the reflection of the region is over here. And we can certainly, rotate. We can get an idea if we add a little more to the graph here. This is a problem where you're going to have an outer volume minus an inner volume. That's the way you want to do it. So the outer volume, we need to find the radius for the outer volume. Well, the radius is going to be this radius here. Okay, because you go from the axis of rotation to the function, and what you're having here is the outer volume looks something like a bowl with a flat bottom. That's what the outer volume resembles. And so the radius would be a difference in x values. Well, you know, you take the right x value minus the left x value to get the radius. Okay, it's no different than if you had like a number line here and you had a 2 here and a 7 here. What's the distance? Well, the distance is 5. And how do you get 5? You take 7 minus 2. So it's the right, you know, x value minus the left x value. We're doing the same thing here. The right x value is determined here. Well, that's on the parabola y equals x squared, but that means x equals root y. And then the vertical line gives you the other x coordinate. This point here has x coordinate x equals -1. So the difference in the x coordinates, the difference in those x coordinates has to be root y minus a -1, which is the same as root y plus 1. Okay, and that's why when you look below, the outer volume, the radius is root y plus 1. The inner volume is going to be, let me just, okay, the inner volume is, I'm sorry, the inner radius is this radius. So you're going from the axis of rotation to the function x equals y squared. So the difference in those x values is y squared minus -1. And incidentally, the inner volume would resemble this sort of frustum-shaped, it isn't quite a frustum, I guess, but it's like a kind of a vase, I guess. And the inner volume is y squared plus 1, because here is the radius for the inner volume, y squared minus -1. So you see the pictures really are helpful. Pictures are really helpful. If you get a good picture, these problems are not that hard to do. The limits are there from 0 to 1, of course, the y limits, because the points of intersection on the region go from the origin to the point 1, 1. So y values go from 0 to 1. It's not too hard to, well, what I'm trying to say is the integration is not that hard in these problems, but what is a little bit of a challenge is finding the right, finding the right way to get the volume. But if you draw a picture and you're careful about it, you can get the right expressions, and then it's just a matter of integration. Okay, so if we go to the next page, I actually worked through the integration for this problem. Root 1, we had for the outer volume, we had root y plus 1 quantity squared. Okay, and so I'm going to FOIL that out. And for the inner volume, the radius, should say the radius was y squared plus 1 squared. So again, I'm going to FOIL that out. And, then this is just basic integration, stuff you learned in Calculus 1. You just, get your antiderivatives, substitute in 0 and 1, and work it out. Okay, you just be careful. You just be careful about, what you're plugging in there. When I plug in the 0 in the antiderivatives here, when I plug in 0 in the antiderivatives, I'm going to just get 0. So I just put a 0 there and a 0 there. Okay, and if we move to the next page, then I write the volume, I write out the fractions, I get common denominators for the fractions, and I work it out. This is something probably that, I mean, I'm showing all the little steps here. You could get that volume. I mean, like the TI-83, 84 calculator can take fractions with different denominators, add them, and get a common denominator fraction with the common denominator, or simplified fraction. It's not hard. The math's not hard, but the volume is going to be 29 pi over 30. So whether it's 29 times pi over 30 cubic inches, cubic feet, but it matters, right? It does matter because, if this is a product where you're creating volume, you want to know the exact volume because that will affect the cost of making the product. Okay, so, you're not interested in an approximation. If you can get the exact value for the volume, that's great. All right, so I hope this is helping. I hope this is helping. I'd like to do one more example with you, and again, just pause the video if you need to, if you need to, think about things. Okay, so, all right. Let's go ahead to one more example here. Here, we want to find the volume of the solid obtained by rotating the region enclosed by these curves about the line y equals 2. So you have y equals 2 plus the secant of 3x, where x is between negative pi over 9 and pi over 9. And then you have the horizontal line y equals 4. So there's a region enclosed by these two curves, and we're going to rotate that region about the line y equals 2. Now, this y equals 2 plus secant of 3x, you can just think of that as 2 plus 1 over the cosine of 3x. Okay, which might make it easier for you to graph like in Desmos or on your TI-83, 84 calculator. All right, so the first thing we have to do is we have to draw a picture of this problem. You're not going to easily get the right answer without a picture. Okay, these problems require a picture, and I would be looking for pictures on the exam as well. Okay, all right. So, right, and your exam's coming up, right? On this Thursday, October 7th. So, okay, here's a picture. Okay, and so 2 plus the secant of 3x is here, and you have to make sure your calculator is in radian mode. And then y equals 4 is here, that horizontal line. And this is the region you're rotating about the horizontal line, y equals 2. And so the reflection of that region will be this region. And the volume that results by taking this, like orange peel, looks like a piece of an orange, and rotating about that line y equals 2. If you were to take the volume of a can, okay, this is your outer volume, the volume of that can, and then subtract the volume of like a spool, the sewing spool, Okay, so you can see the can would be the outer volume in the picture, and the sewing spool would be the inner volume. That'll get you the volume you're interested in. So now, of course, how am I getting these intersection points here? Well, I gotta set the secant. Well, the 2 plus secant of 3x I set equal to 4. And so secant of 3x equals 2. 1 over cosine of 3x is 2. Cosine of 3x is a half. 3x is the arc cosine of a half. So the arc cosine of a half, well, the arc cosine is positive in the first and fourth quadrants. So the arc cosine of a half would be plus or minus pi over 3. 60 degrees pi over 3 gets you in the first quadrant. Negative 60 degrees, which is negative pi over 3, gets you in the fourth quadrant. And incidentally, you know, if you think about your 30, 60, 90 triangle here, since the cosine of 60 degrees, which is adjacent over hypotenuse, is you know, 1 over 2. So that's, you know, the pi over 3. So you divide then this equation here. You got to divide this by 3 to solve for x, and x will equal plus or minus a ninth. And so that gets you these intersection points of negative pi over 9 and 4, and pi over 9 and 4. Okay. Now the outer and inner volume, again, since you are rotating about this horizontal axis, y equals 2, the area is going to be a pi r squared. So you got to get your outer and inner radius. Well, for the outer radius is simply going to be this value here minus this value, and that is 4 minus 2. So for the outer volume, you're going to have 4 minus 2 is 2, so the radius is 2. So the area, the A of x, is equal to pi times 2 squared. That's for the outer volume. Now the inner volume, okay, let me just clear that. The inner volume is this volume here, right? From here to here. And that's going to be the function 2 plus secant of 3x minus 2, which is secant of 3x. And that's your radius. And so the area for the cross-sectional area for this spool here would be pi times the secant of 3x squared. And your limits go from negative pi over 9 to pi over 9. Okay. So when you rotate a region about the x-axis, or I should say a horizontal axis, you're going to integrate with respect to x, because the cross-sectional areas are functions of x. But like in the previous problem, if you rotate about a vertical line, I can actually go back to that real quick. If you rotate about a vertical line, then cross-sectional areas are functions of y, right? They're functions of y. As y changes, the cross-sectional area changes. But on that note, let's go ahead and finish up this problem. So the problem we were looking at now, here's the expression for the volume. You got to get that first. Okay, and now if we work through the integration, it's not that hard. the secant squared of 3x, I just do a substitution. I let u equals 3x. And so the top x limit, pi over 9, becomes a u limit of pi over 3, because 3 times pi over 9 is pi over 3. And similarly, the bottom x limit of negative pi over 9 would become a u limit of negative pi over 3, because that's just 3 times pi over 9, negative pi over 9. Sorry, let me rewrite that. Yeah, this is 3 times negative pi over 9. That equals negative pi over 3. And 3 times pi over 9, for the top limit, is pi over 3. So your new u limits are pi over 3 on top, negative pi over 3 on bottom. And the first integral is easy, right? And the antiderivative of secant squared of u is the tangent of u. That's one that you should always know, right? And so you evaluate your integrals, and your final answer for the volume, and this is what WebAssign would want, is 8 pi squared over 9 minus 2 pi times root 3 divided by 3. Okay, and that's a positive volume, by the way. Our volumes are positive for these problems. Okay, so I hope this was helpful. And if you have any questions, please see me at office hours or after class, okay? And we've now, you've seen a variety of problems, and you should be good to go. You should be, at least, the second assignment has harder volume problems like these, and I think you'll be fine with the help aids, and also I think this video will be helpful. So, all right, well, thank you very much, and I'll see you in class. All right, take care.